All right, welcome to the Explainer. Today, we're putting on our detective hats because a brand new scientific paper has just dropped a huge clue about, well, the end of the universe. And let me tell you, it's shaking up everything we thought we knew.
I mean, it's maybe the biggest question, right? How does this all end? And for scientists who study the cosmos, this isn't some late-night philosophical debate. No, it's a real puzzle they're trying to crack, using hard data, massive telescopes, and frankly, some of the most mind-bending theories in all of physics.
So, let's start with the first clue in this mystery. It's something that sounds simple, but is actually, well, it's completely baffling. We've known for a while the universe is expanding, but the crazy part? That expansion is speeding up. It's like something out there has its foot slammed on the cosmic gas pedal, and galaxies are just flying away from each other faster and faster every second.
And this mysterious driver? Scientists have a name for it, even if they don't know what it is. They call it dark energy. And get this, it makes up something like 70% of, well, everything in the universe. It's the biggest piece of the cosmic pie, and yet we have basically no idea what it is. So, you guessed it. This is our prime suspect in this cosmic whodunit.
So to really get why this new evidence is such a big deal, we're going to get familiar with the reigning theory. You could call it the usual suspect in this whole investigation.
That theory is called the ΛCDM model. Now, that first part, lambda, that's just a Greek letter scientists use for what they call the cosmological constant. And for a long time, this model has been incredibly good at explaining the universe. Its main idea is that dark energy is, well, constant. It's a steady, unchanging force that's just always there, pushing everything apart with the exact same oomph forever.
But the case is definitely not closed. While this model works for most things, some cracks are starting to show. The big one is something called the Hubble tension. Let me put it this way. Imagine you're trying to figure out how fast a car is going. If you look at the speedometer, it says one speed. But if you calculate its speed based on where it started and how long it's been driving, you get a totally different number. That's what's happening with the universe. Our measurements of the expansion rate now don't match the predictions from our model based on the early universe. It's a huge problem, and it means our usual suspect might have some holes in its story.
And this is where things get really interesting, because that brings us to the brand new evidence that's shaking everything up. A new piece of the puzzle just landed on the table, and folks, it is a big one. I want you to meet DESI. That stands for the Dark Energy Spectroscopic Instrument. For the past few years, this thing has been working like a master map maker, building the single largest, most detailed 3D map of the universe we have ever had. I mean, we're talking about an unprecedented look back through the entire history of the cosmos. And this image, this is a great look at how the actual detective work gets done. You've got these different theories, those are the colored lines and splotches, and scientists are basically checking to see how well they fit the actual data. They take clues from the baby universe, from right after the Big Bang, which we call the cosmic microwave background, or CMB. Then they compare those clues to the newer evidence from our more recent universe, which is what DESI gives us. The huge question is always, does the story check out? Does it make sense across billions of years of cosmic history?
And here's the bombshell. The brand new data from DESI is suggesting that maybe dark energy isn't constant at all. It might actually be changing over time, getting stronger or weaker. And if that's true, well, that means our prime suspect, that unchanging cosmological constant, might just have a solid alibi.
So, if the standard model is on shaky ground, what's the alternative? It's time to meet the challenger. There's a new suspect in town that's been waiting for its moment.
This challenger theory is called holographic dark energy, or HDE for short. Now, this is a pretty wild idea, I'm not going to lie. It comes from some really deep, fundamental physics, trying to connect the energy of empty space with the rules that govern black holes. But look, you don't need a PhD to get the most important part. The key takeaway is this. In this theory, dark energy is not constant, and its entire behavior and the fate of our universe all boils down to a single specific number.
And the stakes could not be higher. That crucial number is called K, and you can think of it like a cosmic switch. If K is just a little bit greater than 1, dark energy is a pretty chill, weakening force. This is sometimes called quintessence. It leads to a nice, slow, gentle expansion. But if K dips below 1, oh boy, dark energy becomes this runaway phantom energy. It gets stronger and stronger over time until it literally tears everything apart. Galaxies, stars, atoms, the very fabric of space-time itself. We call that the Big Rip.
A tale of two universes. You got it. The
The whole investigation now hinges on measuring this one little number, C. But this is where the story takes a crazy turn, because what happens when scientists actually use that new DES data to figure out what C is? Well, it's a real plot twist.
Okay, so first, they look at clues from the more recent universe, data from DESI and from those exploding stars called supernova. And this evidence, it points pretty clearly to a value of C that is safely above 1. So the verdict seems obvious, right? We're heading for a calm, gentle end?
Yeah, you can see it for yourself right here in the data. That black dashed line running across the middle, that's the danger zone. That's the tipping point, the phantom divide. Now look at the orange and green lines. That's the data from our recent universe. See how they're both staying comfortably above that line? It looks like we're in the clear. A safe, quiet future ahead. Case closed. Or is it?
Yeah, not so fast. Because the investigation takes a truly shocking turn when they add in the evidence from the very beginning of the universe. That data from the cosmic microwave background.
Just look at what happens. When you combine all of the evidence from the beginning of time and from today, the whole picture flips. That purple line, that's all the evidence put together. And it just dives straight across the phantom divide into the danger zone. And this isn't some tiny little statistical blip either. The data points to this with a really high confidence. All of a sudden, it looks like our universe is absolutely on a crash course for the Big Rip. The evidence from the past and the evidence from the present are telling us two completely different stories.
So, let's get this straight. The recent universe says we're safe. The early universe says we're doomed. What on earth is going on? How do we make sense of this? Let's get to the verdict. At least, the verdict for now. Well, what if there's a third option? Maybe the Challenger theory just needs a little fine-tuning. Scientists came up with a model called interacting holographic dark energy, and the core idea is pretty straightforward. What if the two biggest mysteries in the universe, dark energy and dark matter, aren't separate? What if they actually interact with each other? Turns out, if you allow for that possibility in the model, the Big Rip suddenly becomes way less likely. This could be the very thing that explains the conflicting evidence.
Okay, so now we've got 3 suspects lined up. We have the standard model, our usual suspect. We have the new Challenger, holographic dark energy. And we have the modified Challenger, the one where dark matter and dark energy interact. To pick a winner, scientists use this really powerful statistical tool called Bayesian evidence. Think of it like a cosmic judge, carefully weighing how well each suspect's story fits all the clues we have from the dawn of time right up to today. And the final verdict is in. And you might be surprised. The original suspect, the standard model, is still the most likely culprit. This chart shows you the results. Basically, the lower the bar, the worse that model fits the data compared to the good old standard model. So, despite all the drama, despite the tantalizing clues from DESI, when you weigh all the evidence together, the simple idea of a constant dark energy still provides the best fit. For now, anyway.
But let me be really clear. This case is far from closed. That tension in the data is still there. Those hints that dark energy might be something more, dynamic, something that changes over time, they are incredibly tantalizing. And with new telescopes and observatories coming online soon, we're about to get even better data that will test our standard model like never before. The most exciting part? We are living in an era where we might, just might, finally unmask what dark energy really is, and in doing so, finally learn the ultimate fate of our universe.